respect of time, I think we'll get started. Got a few attendees, probably a few stragglers coming in, but let's get started. So on behalf of Skanska and JB&B, I want to welcome our participants to today's Module 2. It's the second of a 3-module series related to demystifying carbon in construction. I'll backtrack a little bit. Module 1, which was presented by Molly D of JB&B, focused on operational carbon. Today's focus will be presented by Elaine Lai of Skanska, and it will be more focused around embodied carbon. And then Module 3, which will be a week from today, will focus on some other commercial considerations and some life cycle considerations. So I wanted to start with, talking in the sense of a little bit of context, right? So when Skanska and JB&B first set out to think about this, one of the goals was to understand the opportunity for decarbonization in the construction industry. And it's clear that the construction industry drives global emissions. And with that understanding, achieving sustainability goals will only be possible if the construction industry plays a major role. And we see these initiatives boiling up in several parts of the U.S. And locally and globally, right? New York, Boston have initiatives in place, and I think we'll be seeing much more of this in the coming year. So there are benefits, that we've discovered and talked about, right? Decarbonization initiatives can be cost effective, both in existing buildings and in new construction. And there's a tangential benefit that companies will gain through consumer awareness. And actually, you can make the case that it's been shown that the capital markets focus on high efficiency buildings with lower carbon footprints will put them at an advantage. I want to talk a little bit about the players in the construction cycle, right? But each player, whether it's a designer, an owner, a construction firm, or subcontractors, each play a role in the life cycle and need to support collaborative action to achieve the goals that are being set out. Elaine Lai is going to lead today's conversation, so I'm going to let the panelists introduce themselves. So Elaine, why don't you introduce yourself first?
Thanks, Bob. Again, my name is Elaine Lai. I sit in the Portland office for Skanska in the pre-construction team, also with the Green Project Solutions team. So we support projects all over the U.S. building market for Skanska. Thank
you, Elaine. And today we have Molly D is part of the presentation today, and Molly presented the materials on Module 1. So Molly, why don't you introduce yourself?
Thank you. Hi, everybody. Molly D. Ramasamy here with JB&B. I'm the Director of Deep Carbon Reduction at JB&B, and so my focus is on carbon reduction in both the new and existing building markets. As Bob mentioned, last time we presented on operational carbon, specifically with a little bit here and there on embodied carbon, but today is really about embodied carbon in some more depth. So looking forward to hearing it.
Thank you, Molly. And we don't have Mark Moore with us today, but Mark will introduce himself next Monday in Module 3. So with that, again, as Mike Choquette pointed out, there is a Q&A panel on the lower right hand of your screen, so I'll be monitoring that. So feel free to ask questions as we move through the presentation. And Elaine, I'll let you take it away from here.
Great, thanks, Bob. So just a quick run through of the agenda for today's Module 2. We'll do just a quick overview of the topics that were covered in Module 1 by Molly with JB&B. Talk a little bit about our Skanska's carbon goals, and then focus in on some of the major materials that we tend to work with on our projects, the concrete, steel from the embodied carbon perspective, talk a little bit about environmental product declarations, what they are, how they can be used, and then do a live demo of the Ec3 tool that we co-developed with our partners at Microsoft. So just a quick overview of the topics that were covered in Module 1. We focused, Molly with JB&B focused quite a bit on operational carbon, part of the equation, what it is, how it's generated, and the various dimensions of influence that are driving low carbon consideration in buildings. So from the policy angle, public opinion, technology, and cost. We are, as both Mike and Bob had mentioned, making this available at least internally in the Skanska Learning Center, and we will be trying to figure out how to make this available to external Skanska parties afterwards as well. So if you have an interest in receiving this and you're external to Skanska, send me an email and we will try and find a way to get access to you. So Skanska and carbon, one of the key drivers for us as a company is we have also committed to carbon target reductions. So we originally had made a goal of a 50% reduction by 2030. This is for scopes 1 and 2. And then net zero by 2045. So we, based on the trajectory and how far we've gone, they've actually updated this goal to be 70% reduction by 2030. The goal of 2045 is to include our value chain. And so this is potentially one of the more challenging aspects that we're just starting to get our arms around now. From what I hear across many companies, oftentimes 90% of the carbon embedded in sort of their net zero goal that they're challenged with is that 90% of it is in this value chain. So we'll talk a little bit more about this in today's module. So the carbon emissions in our value chain, so this includes our net zero goal by 2045, includes carbon in the materials that we use. So that is what, when we talk about embodied carbon, and I'll talk a little bit more about this, but it also includes our supply chain, our subcontractors, as well as our construction operations. You may or may not be aware, but last November, to help us get our arms around what this supply chain carbon is, Skanska has committed to conducting embodied carbon assessments for all projects nationwide. So this was to begin in November of last year. So this is all projects that are 50,000 square meters or larger, new construction. So this is a way we are able to start baselining the carbon in the projects that we build, but also helps to provide us better perspective on where the opportunities are on reductions. When we're talking about carbon by sector, building and construction sector accounts for nearly half of all global carbon emissions. When you're looking at the building materials themselves, that makes up approximately 20% of all global carbon emissions. So it's a sizable portion of what we're working with. So today's training is mostly focused on embodied carbon. As Molly had mentioned last week, operational carbon is probably the form of carbon that most of you are familiar with. This is the energy and the emissions related to what it takes to run a building with heating, cooling, the mechanical systems, electrical consumption. On the embodied energy side, this is what some may know as the carbon footprint. So it's the energy and the emissions associated with making a material, to extract the resources, to manufacture the product, and then to install the material. There's typically approximately about a 50-50 split between operational and embodied carbon over the lifetime of a building. However, as buildings become more and more efficient, you'll see that operational carbon will become a smaller portion of the pie, but embodied carbon potentially will have a larger and larger impact on the life cycle impact of a building. Structural materials varies building by building, obviously, but on average, we see that the structural materials represent typically around between 40 to 80% of the embodied carbon of a building project. So the choices in the structural materials that you use can have a significant impact on the embodied carbon of a project. So the key materials that we're focused on for the training today are concrete and steel. Other materials that we are focusing on as we're starting to baseline our projects include asphalt. But when we're looking at alternate scenarios, mass timber is starting to have an increasing prominence in structural materials as well, but that's not a topic we will cover today. So on the concrete side, why cement? So cement is one of the key ingredients that make up concrete. The cement and concrete industry is a major player in global CO2 pollution emissions. If it is the second most consumed resource in the world, second only to water, and it is very energy intensive to produce, as well as emits quite a bit of carbon dioxide as part of the process of manufacturing. Overall, as a material, it's responsible for about 8% of total greenhouse gas emissions. If it were a country, if cement industry were a country, the metric that I always find impressive is that it would be the third largest greenhouse gas emitter in the world, only behind China and the US. So looking further into the cement process, this chart shows the energy and carbon pollution intensity of various stages in the cement manufacturing process. Calcination is the process that's used to produce cement. So in this process, the predominant source of energy, demand, and carbon pollution comes from two sources. First is the massive amount of energy it takes to heat the manufacturing production processes to between 1,000 to 2,100 degrees Fahrenheit. And then carbon dioxide is released as part of the process. So on average, you're seeing about 86% of carbon pollution from the cement manufacturing process is directly associated with the calcination process. And this is what it takes to make the cement. So the short story here is that anything that can be done to reduce the cement content of concrete goes very far in reducing carbon pollution of concrete mixes. The general rule of thumb we use is that for every ton of cement, approximately 1 ton of carbon pollution is emitted. On average, about 7 to 15% of concrete is made of cement. These are some of the strategies and some of the lowest hanging fruit on what it takes to decarbonize concrete. These are all available out there today. They're great strategies on their own, but they're not mutually exclusive. There's greater carbon pollution reduction if you combine a number of these strategies together, and they can work very well together. These are some of the key strategies, again, to reduce carbon pollution from concrete and the relative abatement costs in terms of dollars per ton of CO2. So you'll see the red arrow points to the zero. This is cost neutral. So anything to the left of this arrow has the potential to actually serve as dollar savings. Anything to the right potentially has a cost premium. So what we see is that substituting out cement with what they call SCMs, or supplementary cementitious materials, these typically are waste products from other industrial processes, but are a great substitute for cement. Other options include that are coming on the market that we're just starting to see include glass pozzolans. So this is from recycled glass, but the most typical SCMs or substitutes for cement include slag and fly ash. This chart that you see is actually a spreadsheet tool. So typically the way we evaluate concrete mixes, we usually rely on official documents that they call environmental product declarations. However, in the absence of an environmental product declaration, because it does take some time to develop those, there are spreadsheet tools available that can give you a really rough sense of what small changes in mix design can have on the overall carbon content of a given mix. So for every pound of cement that you do not use in the mix design, you can save about a pound of CO2 that's not emitted into the atmosphere. So this tool that you see here is just an example of one that one of our partners at ZGF has developed, and I believe they have made it publicly available. We have seen examples where we've got clients who have substituted out up to 80% of cement with an SCM. So we know the substitution can work, and it's been successful on projects that we've seen. Another strategy here is alternatives to cement. So a very common available cement type is what they call Portland limestone cement. It's an alternative to the traditional type 1-2 cement. And we're seeing an increasing availability of this type 1L cement across the US. Typically, you can substitute out a portion of the cement with limestone. So type 1L is substituting cement with anywhere in the range of 5 to 15% limestone. In general, when projects are using this type of cement, the 1L cement, you're seeing an approximate 10% reduction in the GWP. So GWP stands for global warming potential. That's the key measure of carbon intensity. So you're seeing an approximate 10% reduction in GWP for mixed designs that use 1L in lieu of traditional type 1-2 cement. This map that you see is a map of the growing number of states where the State Department of Transportation has either accepted or is currently considering accepting the use of type 1L cement on DOT projects. Another strategy is to upcycle concrete demolition waste in new concrete mixes. So what you probably typically hear is that folks are recycling existing concrete waste in use as base course for roads. That is probably the most common use case that you see. A newer use case that we are starting to see some examples of are taking old concrete demo waste and upcycling that to replace out at least a portion of the virgin aggregate that's used in concrete mixes. Virgin aggregate, as you know, is a finite resource, and mining it has significant impacts on the environment as well as its water resources. Another benefit that they're starting to see and starting to quantify is that recycled concrete aggregate, or RCA, has another benefit, which is that its very nature, as soon as it's placed into service, it sequesters carbon dioxide, so through a process known as carbonation. It's not new. It's inherent in the nature of concrete. As you crush it, the increased surface area allows for even greater area for CO2 absorption to occur. So this is a newer area that they're starting to quantify what this benefit is, but something to keep in mind. An example of where we've used this and actually quantified at least the fiscal savings, Skanska has a project in Florida. It's a 21-mile I-4 highway corridor in Central Florida. Through the use of concrete demo waste from this project, crushing it, and reusing it as road base, they found that it resulted in savings of $2.63 million. So on the fiscal side, there's significant benefits. On the environmental side, that's something we're still working to quantify, but it is something to keep in mind. Time to strength. In our business, schedule and cost are king. Typical mix designs are based on 28 days time to achieve full strength. However, mixes that have a 56-day time to strength can cut carbon pollution emissions by more than half. At first glance, 56 days may seem off-putting. While you may need 28 days data strength for key project elements, you might ask your project team whether there are any elements that could allow for a slightly longer time to strength. So some common elements that we see that could allow for a longer time to strength could include elements such as footings, curbs and sidewalks, and basement walls. But obviously this would be a conversation that would need to take place with your partners at the structural engineering firm. So by identifying elements on your project that allows for 56 days to strength, you open the door for even greater options and opportunities for lower carbon concrete mix designs. And then renewable diesel, this may not be available in all states. We're seeing a growing presence and availability here on the West Coast, where renewable diesel, which is basically, it's not biodiesel, but it is made of it's biologically based. So typically waste products from the agricultural sector. Huge savings in carbon when on the manufacturing side, conventional fossil diesel is substituted with renewable diesel. I'm not sure on the East Coast, but I do know in the West Coast it is can be cost neutral. In some cases it actually could be cheaper than traditional diesel. Why this matters is when you quantify the carbon footprint of a product, so when you're looking at the carbon emissions of the concrete mixes, what it takes into account is the carbon that's associated with material extraction, the transport, and manufacturing. So any one of these life cycle stages where you can substitute out fossil fuel intensive fuels with something that's renewable does have the potential to drive down the carbon footprint of that mix. All of the strategies that I listed prior to this slide are easy strategies we can adopt to reduce carbon pollution in our concrete, but I did want to make mention of new technologies that are either currently available or in development. So just to keep in the back of your mind, we won't delve into these technologies now, but just wanted to make sure that you are aware that there's some other opportunities out there as well. On the steel side, also a major component of the buildings and the projects that we build. Structural materials, as I mentioned, can average between 40 to 80% of the embodied carbon of a building. So this tries to size up, how does concrete size up relative to steel? In general, on a unit basis, steel is much more carbon intensive in terms of pounds of CO2 per ton of steel. But when you look at the total weight of concrete on projects, you tend to have significantly more weight in concrete than steel. So even though steel may be more carbon intensive on a per unit basis, concrete tends to make up a much larger percentage of the carbon footprint of a building. Just a quick and simple, probably the simplest, most basic explanation for how steel is made. It's mixing iron and carbon at very high temperatures. So virgin steel is typically made through a two-step process. The first is to produce iron by using a blast furnace. The iron is then converted to steel in a basic oxygen furnace. So BOF is a typical acronym that I'll reference here. Recycled steel, this is also very common, but this is produced in a different type of furnace that they call the electric arc furnace, or EAF for short. Why these production and manufacturing pathways matter is that the pathway that you choose entirely drives the carbon intensity of that steel. It's inherent differences in the production processes at play that directly impact and determine the carbon intensity of the final steel product. So as outlined here, about 40% of US steel production we use the basic oxygen furnace, or BOF for short. These are typically larger plants, typically also powered by fossil fuels. For those that are using recycled materials, you can see that it can incorporate about 25 to 35% recycled steel as part of that process. The typical shapes that can be produced in the BOF, the basic oxygen furnace, are HSS, deck materials, studs, and plate. However, any shape can be produced in the basic oxygen furnace. The electric arc furnace, you're seeing a larger number of these plants in the United States starting to put in place EAF. They tend to be smaller plants, and they tend to also be powered by electricity. So the carbon intensity is largely dependent on where you're located and the grid mix in that location. Up to 90 to 100% recycled materials can be used in the electric arc furnace. On structural steel, you're seeing that average be about 93% recycled product. And the shapes that tend to be manufactured in these EAFs are rolled shapes, plates, and rebar. Delving a little bit further into the environmental impacts, BOFs rely predominantly on combustion fossil fuels, often to heat the furnace above 2,600 degrees Fahrenheit. Again, as I mentioned, the EAFs, electric arc furnaces, by its nature, powered by electricity. So again, the carbon intensity is largely determined by the grid mix in that region. Fossil fuels in EAF steelmaking accounts on average about, in the US, about 33% of the grid mix. The Pacific Northwest we're seeing is some of the cleanest because such a large role that hydropower has. The amount of CO2 emissions per ton of crude steel from the BOF and EAF steelmaking on average, if you're comparing the two, the blast oxygen furnace, or BOF, on average is about 1,149 kilograms of CO2 per ton, versus on the EAF is about 47 kilograms of CO2, so a little less than half. Let's see. On the design side, again, shapes, there's some shapes that can only be produced from electric arc furnaces. So by prioritizing, when possible, shapes that can come from electric arc furnaces, you basically have the opportunity to use much lower carbon intensity steel. But engaging your structural engineer and your architect is really important to explore where these opportunities are. Things that I won't talk about much here. You're seeing a growing interest in substituting out steel with mass timber. Mass timber, being a biological resource, has substantially lower carbon intensity than steel. Also, you're seeing that domestic steel tends in general to have a higher percent that's produced in EAFs. Often you're seeing foreign steel can be cheaper, but with shipping costs increasing over time, in some cases foreign steel may not necessarily be cheaper. So this is a constantly evolving landscape. But important to really understand this, you will have to ask for mill-specific environmental product declarations to get an actual sense of what the carbon intensity of that material is. So going through environmental product declarations and the Ec3 tool. Environmental product declarations is the key document that we rely on to get a sense of what the carbon footprint of a material is. So given the myriad of strategies that suppliers can take to reduce the carbon intensity of their mix options, it's really important to be able to have something like an EPD to rely on to get a more accurate sense of what that carbon footprint might be. So what we commonly liken what environmental product declarations are, they're really similar to how you might approach a nutrition label on a food product. A sense to a way to give you a way to compare apples to apples between concrete mix designs or various materials, whether it's insulation, steel, etc. So EPDs are an internationally accepted, verified, published report that quantifies the impact that a product has on the environment. So one of the core metrics is GWP, which stands for global warming potential. But it also includes other metrics such as acidification, nutrients input to waterways, which cause oxygen depletion. So there are other metrics, but what we focus largely here is on the global warming potential. They're not to act as product ratings, but they're intended solely to serve as an informational resource that helps architects, designers, specifiers, and other purchasers better understand a product's environmental impacts. Typically, a third party is brought in to develop an EPD for a product. For concrete, there are a few entities that focus exclusively on developing EPDs for concrete. Why this is because typically once you have a model that's calibrated to a given facility, some of these providers, one of which is Climate Earth, can offer what they call an EPD generator. So once the model is calibrated, it makes it really easy to start generating EPDs on the fly based on small shifts in mix design for a project. But to create and calibrate the model, it can take upwards of 8 months to a year to finalize an EPD. They do spend about 60 to 90 days to collect data. It does have to go through a verification process as well. Now that we have all these EPDs, how might we use them to help inform decision making? Ec3, or the Embodied Carbon in Construction Calculator tool, is a free and open access tool that was co-developed by Skanska with Microsoft and was intended to support procurement decisions. In essence, Ec3 is a database of all of these EPDs. Users can use the tool to calculate upfront embodied carbon emissions associated with material decisions. It also allows teams to evaluate alternatives with lower carbon pollution intensities. A key functionality of the Ec3 tool, one of its main features is to help users be able to find and compare materials. Other scenarios include the ability to compare scenarios if there are different options for how you might choose to build your project. A new functionality that was just incorporated this year was the ability to level bids within the tool as well. There's a lot of great resources and trainings available on the Building Transparency site. So just a quick run through before I go into the live demo. This is a quick snapshot of really how Ec3 works. So what we take is the material quantity estimate. So this is what we would look for folks that are, when we're baselining our projects, the key information that we look for to pull from our estimates. So that material quantity estimate is then multiplied by the embodied carbon for that material. So that then pulls from the data that's within Ec3 to give you the overarching embodied carbon estimate of whether it's that material or for that project overall. So I'm going to turn my video off because it gets pretty glitchy trying to run Ec3. Let's see. Trying to close out PowerPoint to open up Ec3. Okay, so once you sign up for a free account, just running through some of the functionality here in Ec3. This find and compare materials is a really great place to start. We have different, regionally we have potentially more EPDs for concrete in some parts of the country than others, but this is growing by the month. There's as more and more companies are uploading their EPDs into the system. So if once an EPD is developed, we then look for the supplier to upload this into the system for us to be able to access. These are the material types. A lot of those of the pilot category may not be accessible to new users, but the key product categories, material categories that you can use and Ec3 are listed here. The ones that are most common that we tend to use include concrete, steel, insulation, cladding. So just to give you an example, if you're looking on the concrete side, what I typically do, I mean, there's a lot of different variables that you can toggle if you have specifics that you want to look for, but typically I do a search based on compressive strength as well as location. So if you're, for example, looking for 4,000 PSI mixes located in Oregon, you also have the potential to input your address of your project, and you can set limits to say, well, you're only interested in suppliers within 50 miles or whatever. You can choose if it's 25 miles of a given project. But for this example, let's just assume we're looking at Oregon. So it'll walk you through selecting that under geography, compressive strength here. When you hit search, sometimes it takes a little bit of time. It will pull all the EPDs that have been uploaded into the system that meet the criteria that you've input here. Let's see. So that search was able to pull up about 463 EPDs that match the criteria. So this, when you're looking at the basic statistics of across the 463 EPDs, what you're seeing is an average carbon intensity of 861 kilograms of CO2 equivalent. What's achievable, so this achievable number is basically the 20th percentile of all 463 mixed designs that were evaluated. The conservative number is when you're looking at kind of like the 80th percentile. So this is a graphical depiction of what that looks like. So the average here would probably be, for some reason, I don't know how it's getting 861 because it looks like the average should be less, but this kind of shows the range of the minimum and the maximums that they're seeing of the EPDs in the system, along with the conservative and the achievable, the 80th and the 20th percentile. This functionality here, you can compare companies by clicking this compare tab. It breaks this out based on the suppliers and how they compare with each other. So this is kind of why we hope suppliers will upload their data into the system, because when you've uploaded your EPD into the system, at least your products then can show up for when we are in the procurement process, when we are looking to see what's out there. So this kind of shows you for all mixes that were designed by Cadman, what kind of that range looks like. You know they've got options here, 178 mixes that have a carbon intensity of 178 kilograms of CO2 per cubic yard. But obviously you have to look in more detail as to what type of that mix that is and if it fits for your project. So that's an interesting option there. You can also compare within a given supplier. They may have different plants. You can compare it by location. If you were wanting to compare buildings, a quick walkthrough here of how we've used it to start baselining our projects. So for those in Skanska, we've created templates that are easy to copy and paste. So each of our project offices has a folder. Inside that folder will be a template. that you can easily just copy, so you don't have to create it from scratch. To do a copy of the template, or you could just use an existing project. This button here allows you just to copy everything from that template, and you can upload it with your own material estimates, quantity estimates. So one example here for a project that we have, the first, you would input as much detail as you can about the project. It's not crucial, but as much data there as you can input is helpful. So we started to include basically the key elements for the major materials on our project. So that's steel, asphalt, and concrete. That's what we're tracking for all of our new projects, over 50,000 square meters. So on this side, what you have done is we've broken this out by elements. So for example, the mat foundation. In cases where we don't have an EPD, for example, we'll just take the entire average of a collection. So here, for example, we're taking all the EPDs. So it can be common in certain states that you don't have an EPD for the supplier you're working with. So what we then use is the average of an entire range. So we just, in this case, you would select the entire range. So the carbon intensity is this average number. However, if you actually have selected a supplier, you can sorry, it's kind of slow. Here, once you have selected an actual supplier and an actual mix, you can click this selected materials after the project is built and go back in there to identify the specific mix design that was actually used. So you'll have to do a search for basically the basic metrics, and then once the list of suppliers and mix designs pulls up, for some reason it's frozen. Let's try it again. So once you find the actual mix that was used on the project, say you decided to go with this specific mix, you would just click a star, say that was selected. So that note tells EC3 that was the actual mix that was used, and then you would click change this element. So this will update EC3 for your project for what was actually used on that. So you'll see that a lot of these, no material is selected, so they're using the average of the entire collection that meets the criteria. And once you have selected the actual material that was used, you can update EC3. Another functionality that's really helpful is the ability to compare scenarios. So in this case, you can, if there are different ways that you've designed it, you can compare the carbon intensity of various scenarios. You can copy and paste, so you don't have to develop a new EC3 for each scenario. The same copy paste function, you can copy and paste and just rename it with the alternate scenario and just update the sections that have changed. So for this example, if you wanted to compare scenarios of the same building, you just click the two, or you could compare multiple scenarios. You just click compare buildings, and it kind of it shows you what the carbon intensity of the different scenarios are. The solid bar is what's achievable. The way it's designed is the top bar here shows what the way it's designed if there's no specifications made for lower carbon options. So in this example, it shows you where the opportunity is for carbon reductions. You can look at it in terms of material category. So between the two scenarios, you see that the concrete plays the biggest role in terms of carbon intensity of that project, based on the input that you have evaluated. One thing I forgot to show you was once you have input your project into Ec3, what is really helpful is the summary data. So this button shows you a summary, what they call the Sankey diagram, of all of the components you've entered, where the opportunity is for savings. So overall, you're seeing that if you are mindful with how you specify materials, there's a potential for a 43% reduction in carbon for this project. And this kind of lays out where these savings would come from. So again, the full bar represents if no specifications are made, that's kind of the business as usual case of what that carbon intensity for the ready mix might be, or rebar. The solid bar is what the opportunity is for carbon savings if you were to specify a lower carbon alternate. So you are also able to break this out. This download reports will break it out in terms of quantities based on the major materials that are used. So these are great ways to just kind of summarize where you are with the given project. So this has broken it out into the quantity of each of the major materials that we looked at, along with the carbon intensity. This baseline is kind of like the business as usual. The achievable is the 20th percentile of what is potential reduction could be. So I think that's kind of the key use cases here. I'll show a little bit about the bid leveling function next week. But I think that kind of captures the live demo. There's a lot of new functionality. It seems like every month they add new functionality to Ec3, so it's always an evolving process. But the basic functionality being the ability to compare materials, compare suppliers, compare scenarios. So I hope that was a good, at least, overview of how it can be used. And there's a lot of demos, both on YouTube as well as on the Build-In Transparency site, if you want to dive into any of those in greater depth. So I think that is it for me. Can open it up for questions.
Yeah, so thank you for that, Elaine. That was incredibly informative. We do have a few questions. The first one relates back to a map of the U.S. that you showed at the beginning of your discussion regarding adoption of Portland limestone cement. And the question posed, most of Northeast appears to be considering. Why the lag in adoption here versus the remainder of the country?
That's a good question. I don't have an answer for that. It's because I think that's a decision process and evaluation process that is taking place outside of anything Skanska is involved in, but at the state DOT. I can look into that to try and get a better sense of what it takes to get it approved, but I think state by state there's different approval mechanisms and timelines for how they approve mixes for DOT projects.
Yeah, well, actually, that raises an interesting point, Elaine. So, and the example you used in the Ec3 demonstration, clearly Portland as a home market has advanced this thought considerably. If you think back to how Portland got to where it is today with, certainly on the concrete side, who were the early adopters, or what forces within the market pushed that adoption? Was it more public works, private, or some combination?
I definitely think it's a combination. As you see projects start requiring that, we have certain projects start requiring that as part of, whether it's a selection, once contractors or suppliers are selected, some projects require EPDs be developed. So once an EPD is developed for a project, typically that company will have the ability then to continually generate that for new mix designs. So both in terms of projects, it could be in the public or private sector, as you're seeing buy clean legislation get passed. That's going to be a huge driver for an influx of EPDs for companies that may not have considered it. Other things, once suppliers see that their competitors are showing up when we're doing searches for material types, kind of has a great, I don't know if you call it FOMO, but they want to also be known, to show up alongside their competitors. So I think it's a mix. There's definitely the key initial drivers are projects, but as we've been rolling this out market to market, what we like to show is, who of their competitors are already showing up in this database, and that if they want to be considered alongside their competitors, they might consider investing in developing an EPD as well.
Thank you for that. And we have a two-part question. I'll start with part one. How does a manufacturer obtain an EPD certificate?
Sure. An EPD, it's a pretty complex process, but the key steps is hiring on a third party to help develop a model of the manufacturing process at the facility. It has to go through a verifier, so that company that develops the EPD has to then go through a verification process. So there's a number of verifiers that are out there that then walk through the model that was developed to make sure it's accurate. I think the verification process can take, a few months. It varies depending on the workload of that specific verifier. There's a handful of them in the US, but it can overall, from start to finish, take 8 months to a year from developing the model to getting it approved and finalized by a verifier.
So that's, I think you've answered part of this question, but the follow-up was, is there a way Ec3 tool verifies the authenticate of or when a manufacturer uploads it? So maybe that's part of that process.
You can, I don't know that Ec3 does its own verification. We rely on the work that is being done by the verifier. But what you can do is you can actually, it does give you the opportunity to download the actual EPD of a product. So, for example, in this case, all of the EPDs should be available inside this database. So if you have specific questions of a product, you can download that EPD. So you have, if, for example, but I guess to answer the question, Ec3, I'll double check on this, but I don't think we do any independent verification.
Okay.
Kind of intended to just be a database for all of the Ec3s, or all of the EPDs, sorry.
Okay, no, thank you for that. So we have another question related to Ec3, and that is, for the achievable, does that indicate what you could achieve in your local area? Or
for achievable, it means that basically there's a mix design that was identified based on the criteria that you've established in your data pool. So if it was, within 50 miles of your project site, that meets whether it's, 28-day or 56-day time to strength and 4,000 PSI, that there was a mix that was developed that had that GWP, but you would probably need to look at, have a conversation with your structural engineer just to make sure that specific mix design makes sense. But we just know, based on the criteria that was chosen, and there could be differences between all of the mixes that it's looking at, but we know based on those criteria that a mix design was developed that was that specific GWP.
Okay, no, thank you for that. So we're kind of closing in on 2 o'clock. I want to be respectful of our participants' time. So on behalf of Skanska and JB&B, I want to thank Elaine and Molly for their presentations for the first 2 modules. And we look forward to your participation in Module 3, which will be next Monday at 1 o'clock EDT. And thank you all for your attention. Molly and Elaine, thank you for your presentations. And everybody have a great day. Thank you.
Thank you.